Okay, so hi everybody, welcome to our seminar series. We have the pleasure to have with us today Danielle Sponseller. Danielle is a postdoc now at the Chalmers University of Technology. So briefly about Danielle, she graduated last year at the Johns Hopkins University. With a thesis focused on modeling the polarized thermal gas foregrounds for a CMB experiment. And now with this new postdoc, she's working on developing small-scale models of dust and synchrotron emission within our galaxy. So thanks for being with us. The floor is yours.
Great, thank you so much for the introduction and for everyone being here. So today I'm going to talk about a statistical analysis of polycyclic aromatic hydrocarbons, or PAHs, as a potential carrier of anomalous microwave emission. So to start off with some background, so this is a foreground for cosmic microwave background experiments. So the cosmic microwave background is radiation that we see in every direction in the universe, and it's essentially leftover light from the Big Bang. And it's something that can tell us a lot about the earliest stages of the universe. So, for example, we know that matter in the early universe was ionized and making it essentially opaque. So any photons would just immediately be destroyed or scattered. And as the universe has expanded, it's also cooled. And so at some time in the universe's history, roughly 380,000 years after the Big Bang, the universe had cooled enough to form neutral hydrogen, and this is when the universe became transparent to radiation, and we have essentially a snapshot of the universe at this time, and that is what the cosmic microwave background is. The universe has continued to expand, and so the radiation is observed today in microwave wavelengths, and so that's why we call it the cosmic microwave background. It contains a wealth of information about the early universe. So, for example, it's the most perfect black body ever measured and has a temperature of roughly 2.7 Kelvin. And this has provided direct evidence for the Big Bang. We know that it has anisotropies on the order of 1 part in 10 to the 5. And the CMB is also polarized. And one thing that cosmologists are particularly interested in exploring is the potential signature of inflation. And this is a signature that we would see in the polarization of the CMB. So inflation is a hypothetical period of dramatic exponential expansion in the early universe. So here we have sort of a schematic of the evolution of the universe. And so you can see that at modern times, we have this large-scale structure of galaxies and galaxy clusters. And we also have the CMB at 375,000 years after the Big Bang. And before that, we have inflation. And so inflation was proposed to explain a number of oddities that we observe in the CMB. The extent to which the CMB is homogeneous is surprising. So it actually does more than prove the Big Bang. It seems that in any direction you look on the universe, the CMB has reached the same temperature in thermal equilibrium. So this is an unusual aspect. And so inflation would resolve problems such as this and also explain how large-scale structure would have been seeded by, for example, quantum fluctuations in the earliest moments of the universe. So inflation, the reason it would leave a signature in the CMB is through primordial gravitational waves. If the universe did undergo this type of expansion, this would generate gravitational waves, which would then impart a unique polarization pattern in the CMB. So if you have just scattering in the CMB, you would expect a polarization pattern that's referred to as E modes, which is a divergence-only component in the polarization signature. But gravitational waves would rotate this and give some curl component, which is known as a B-mode polarization pattern. And B modes would provide evidence for inflation and also allow us to measure this parameter called the tensor-to-scalar ratio, which quantifies the energy scale of the early universe. So we're really interested in detecting this B mode signature from inflation. So unfortunately, there are many foregrounds that we have to look through when we try to observe the CMB. Many of the most problematic ones originating from within our own galaxy. So we observe within this galactic disk, which contains dust and stars and all these different foregrounds, that can also produce various signatures in the cosmic microwave background, or in our observations when we're trying to measure the cosmic microwave background. So here I'm showing two plots showing foregrounds relevant to the CMB. So on the left, we're seeing foregrounds that are relevant in temperature, and on the right, we're seeing foregrounds that are relevant in polarization. You can see that, so in temperature, there is actually a foreground minimum where the CMB is brighter than the foregrounds. And this has been very useful in being able to take advantage of this to be able to measure the CMB. But in polarization, you can see that the dust and synchrotron dominate over the CMB across all scales. So the focus of this talk is, of course, on anomalous microwave emission, which here is referred to as spinning dust, which I'll explain in a moment. And you can see that it's listed here as a foreground relevant for temperature, but it is actually not a foreground that we can rule out for CMB polarization experiments. So we have upper limits on the polarization of AME. We've never detected polarization, but AME could still potentially be relevant to future CMB experiments. Okay, so what exactly is anomalous microwave emission, or AME? So it was discovered in the context of cosmic microwave background experiments, where basically when we modeled the expected foregrounds, so synchrotron, free, dust emission, and then we subtracted those foreground signals, we saw this distinctive curve that peaked between roughly 10 to 60 gigahertz. And we didn't know what was causing this. And so it was just dubbed anomalous microwave emission, as we didn't have an explanation for it. It was observed to be strongly spatially correlated with thermal dust emission at higher frequencies. However, our models of dust, based on our understanding, suggest that dust emission shouldn't be that bright at these frequencies. So we think it's unlikely to be due to thermal dust. So this is how it was discovered. Here I have two figures. The one on the left is showing a map of the anomalous microwave emission, and the one on the right is showing the Planck 857 gigahertz map, which traces the thermal dust emission. And so the AME map that I'm showing here also is at 30 gigahertz. And even just by eye, you can tell that they're extremely well correlated with each other. So to give you an example of what these spectra look like, so here's a spectrum that's sort of like the poster child of an AME detection, looking towards Lambda Orionis. And so you can see the the dashed component is modeling the free emission. The dotted component is modeling the dust, and there's this dot dashed component, and that is this very prominent excess emission. And so that's a very clear example where we have anomalous microwave emission occurring. So currently, we don't know what is causing this emission. There are many different possible candidate emission mechanisms. So one is that it could be electric dipole radiation from spinning dust. And so the idea there is if you have dust grains with some electric dipole, as they spin, they'll produce this emission, and models of this have shown that it can reproduce the AME spectrum. Alternatively, it could be magnetic dust, either due to spinning grains with a magnetic dipole moment, or it could be thermal emission from grains with magnetic inclusions. It could be thermal emission due to amorphous grains, or a consequence of the two-level system structure that some amorphous grains exhibit. It could be stochastically heated very small grains. It could be free emission from the warm interstellar medium, or it could even be optically thick synchrotron emission. However, most of these candidate emission mechanisms have been strongly disfavored through observations. So for example, if it were due to magnetic dust, we would generally expect there to be fairly good dust grain alignment if it were magnetic, and that would lead to a fairly strong polarization. And current observations have placed an upper limit of the AME polarization of 1%. So it is unlikely to be due to magnetic dust. It's very unlikely to be due to synchrotron emission. This would require extremely high brightness temperatures, And it's also been shown that free emission is just, there are very few environments where that's likely to be produced the AME spectrum. So currently, the best candidate is spinning dust emission. So just to give you an idea of how much the spectrum can vary depending on different factors, we have several figures here that are showing different SEDs for anomalous microwave emission for different dust properties and environments. So in the top left, we have SEDs that show how the spectrum can change when the distribution of dust grain sizes changes. So as we go from red to black, the distribution is leaning towards larger and larger dust grain sizes. And you can see that that causes a trend in the anomalous microwave emission to peak at lower frequencies. And it also changes the characteristic shape of the AME spectrum. The panel at the top right shows different SEDs for sorry, hold on, I actually forgot what this model is showing. Sorry, I'm blanking on that right now. The panel on the bottom left is showing the SEDs for different charges. So the blue and black curves are for positive and neutral grains, and you can see they have a fairly similar spectrum. And the red curve is for negatively charged grains, and you can see that that significantly changes the AME spectrum and expected peak frequency. And the panel on the bottom right is showing SEDs and how they vary with different astrophysical environments. So here we're showing different SEDs for the cold and warm neutral medium, the warm ionized medium, molecular clouds, reflection nebulae, photodissociation regions, and all of these regions have different environmental factors that cause the SED to look wildly different. And so the actual spectrum of the AME can vary significantly depending on what the carrier actually is. And this is important for CMB experiments as we need to be able to very accurately model the spectrum, or else this can directly bias the recovered CMB spectrum. But we don't currently know what this carrier is. So currently what we do is we generally fit a 1 or 2 component AME model, where that basic template is based on assuming that it's electric dipole radiation from spinning dust grains. This can be modeled fairly well with a log normal distribution in log space. A log Gaussian and log space. And basically we fit 2 components by just translating this template in log space. And effectively, this parameterizes the width. But this is a very unphysical model. It doesn't really account for intrinsic variations in dust properties or astrophysical environments. And it's been able to fit these residuals fairly well so far, but it's not really physically motivated, so it could potentially lead to bias in future CMB experiments. So if AME is indeed caused by this electric dipole radiation from spinning dust grains, the most promising candidate carrier would be polycyclic aromatic hydrocarbons. So these grains are very small, which is important as the grains must be small to be able to rotate fast enough to produce AME at the observed peak frequencies. And essentially, they're these rings of carbon atoms with hydrogen atoms at the peripheries. One reason that they're a compelling candidate for AME is that they're known to be ubiquitous in the ISM. And while many PA grains don't intrinsically have electric dipole moments in astrophysical environments, you can have carbon substitutions. For example, a carbon atom can be replaced with a nitrogen atom. And these substitutions can give rise to electric dipole moments large enough to account for the observed excess emission. So this is a sort of characteristic PA emission spectrum. PAs are really a category of grains, and there are many different species of PAs. And so depending on the relative abundances of different PA species, the actual peaks of these different features that we see from PAs, like the ratios of these peaks can change. But you'll notice there's this very prominent peak at roughly 3.3 micrometers. And so we were really interested, okay, could we fit for the PAW distribution on the sky by isolating that 3.3 micrometer feature? And if you look at the first 4 bands of the Derby experiment, one of them coincides perfectly with this PAW feature. And the nice thing about the other 3 bands is that they contain essentially only PAW continuum emission. They contain almost none of the other PAW emission features. So we were really interested in using this to see if we could do a fit that allowed us to separate out the PAW 3.3 micrometer component. So here's an actual look at those first 4 Derby bands. We did use the maps that have already had the zodiacal component subtracted. But as you can see, in band 4, there is a bit of, well, it's difficult to see here, but along the ecliptic plane, there is a bit of excess zodiacal emission. So because we saw that there was still some residual zodi in there, we fit for the zodi as well. So to elaborate more on our fitting technique, what we wanted to do is perform a spectral fit over these 3 components, so PAW, starlight, and zodiacal emission. And we used a linear least squares method to optimize the amplitudes. So for the starlight component, we used the faint source model, which is a statistical model of the starlight distribution in the Milky Way. And for the zodiacal emission, we used the Kelsall zodiacal emission model. And so we fit these components. We did keep the PAW and starlight amplitudes positive, although we allowed the zodiacal component to be negative to correct for any over or under subtraction of zodi from the original maps. And so once we performed this LLS fit, so here's just a look at some of the components that we get out of this. So this is the residual zodiacal emission map. You can see that it does seem that it found some residual zodi that was still in there. There is some component that's being picked up near the galactic center. So it's definitely not perfect, but we did capture some of the excess zodiacal emission. This is a starlight map that we get in band 3. This looks like a fairly reasonable fit to the starlight component. And finally, this is the PAW map that we got. There are some flaws with this map, but this is sort of a preliminary full sky PAW mission map. You can see some artifacts around the galactic center. Part of that may be because of the strong zodiacal emission that was fit there. But you can see that essentially we can fit out the PAW 3.3 micrometer emission and see these features on the sky. So what we wanted to do was use this map then to do a spatial correlation analysis of AME in several different regions on the sky. So the Planck collaboration identified 98 AME sources. And we wanted to try to use these sources to do a spatial correlation analysis because previous studies that have tried to examine these possible connections have generally only focused on one or a couple individual regions and have not really done a statistical sample. The Planck team did compare statistics across this sample. So like they performed aperture photometry on each of these individual sources and sort of compared across the sample, does the AME correlate with PAW emission? But they did not look at the spatial correlations within each individual region. So that's what we wanted to do. We wanted to really look at these smaller scales and see if there was a correlation. So to give an example, here I highlight 2 of the regions. So the row on top is showing Lambda Orionis, and then the bottom row is showing the Perseus molecular cloud. Lambda Orionis was actually somewhat unusual just because that's such an extended region. Most of the regions that we looked at, we used a 4x4 degree square patch on the sky. But for this particular region, we used a much larger area because it's an extended region. But it's one of the most well-studied regions, so I wanted to include it. So you can see from the figures on the top row that this ring structure of lambda Orionis appears in all of these components, although it is much fainter in the PA emission component. But if you look at the Perseus molecular cloud, for example, you can see visually that the AME and PA emission look similar, whereas the structure in the dust emission actually looks considerably different from the AME. So then, to perform a statistical analysis, we use the Spearman-Vank correlation coefficient on the AME versus the dust, or the AME versus the PA emission for each region. Again, I'm showing the lambda Orionis and Perseus molecular cloud examples here. So on the top row, we're looking at lambda Orionis. The correlation coefficient is in the top left of each panel. The left column is showing the correlation between PA emission and AME, and the right column is showing the correlation between dust and AME. And by dust, I mean the thermal dust from larger grains. And you can see for lambda Orionis, it's much better correlated with thermal dust. But for the Perseus molecular cloud, it actually is better correlated with the PA emission. So in addition to just saying, okay, this is better correlated with dust or better correlated with PAs, we also wanted to see how robust that was. So we performed a bootstrap analysis on each of the individual regions. This is just one example looking at the Perseus molecular cloud. And so, for example, this is the distribution we get for these Spearman correlation coefficients. And you can see that the AME dust distribution is fairly well separated from the AME PA distribution. So in this case, this is a pretty clear example where the correlation, where the AME prefers PAs as a potential tracer over thermal dust in this region. So we did this for all 98 sources on the sky. Here again, these circles are showing the 98 Planck sources. But the circles indicated in red here are showing those which were better correlated with PAs. And so what we found was that 17 of these 98 sources actually prefer PAs as a potential tracer. And so this is a non-trivial subset, even if most of the sources are better correlated with dust emission. We did also consider that only some of the Planck sources were considered to be highly significant AME detections. So 27 of those samples were originally deemed to be detected at high significance, where the criteria for that was that the AME detection had to have a sigma greater than 5, but also they ruled out any potential free contamination. And so when we look at only these 27 highly significant sources, we find that 10 of them prefer PAs. And so they're 37% of the sample is preferring PAs. And so it seems when you go to more significant AME regions, it seems there's a greater tendency to be correlated with PAs over thermal dust emission. It's also notable that most of the sources which favor PA emission are further from the galactic plane. And this is because in the galactic plane, you have significant free contamination, and this is one of the more difficult components to separate from the AME. So there's some potential suggestion there that if we have better AME maps or better able to subtract out the free emission, we may actually find that PAs are a better tracer of AME. Finally, one thing that I tried to do was I tried to do a rough correlation analysis over the full sky. So I divided the sky into sort of a coarse-grained heel-pix grid, and then I used the subpixels within each of those larger pixels to do a spatial correlation analysis. These regions are fairly large. They are larger than the region sizes that we used for the Planck sources, but you can see that it seems to practically eliminate the preference for PAs. So the pixels that are reddish here are the ones that favor PAs, and the ones that are bluish favor thermal dust emission. So it looks like when we go to more diffuse emission over the full sky, again, it seems that thermal dust is a better tracer than PAs pretty consistently. But something we want to explore more in the future is how well these correlate over the full sky. And also we want to be able to look at smaller scale behaviors. So to summarize, so of the 98 Planck sources, 17 of them preferred pause as a tracer. And then of the significant ones, 10 out of 27 or 37% of them favored PAW emission. One caveat is so the Quixote team also looked at a subset of those Planck sources and they revised the estimates of the significance for the AME detections. And they were able to really significantly detect AME in many regions where Planck wasn't. And so something I tried doing was just replacing the AME significances from Planck with the Quixote ones where applicable. And when I do that, then I find 43 significant AME regions, 17 of which prefer pause. So that's basically proportional. So 39% of them seem to favor pause as a tracer. Still, it doesn't seem we can point to any single constituent of the ISM and say AME is definitely coming from this source. So in the future, we want to do further work on analyzing the AME in diffuse regions on the sky, and also in looking more into small scale behaviors and how the environmental factors can influence underlying emission mechanisms. All right, thank you.
So question here. Yeah.
Hey, thank you very much. Very interesting. So just a clarification, when you talk about past, basically you only mean the 3.3.
In this case, the 3.3 feature, yes.
Okay, because you have a band there. Okay, so don't have any, I don't know. For future works, do you have planned to also see the correlation with the 6.2 or the 7.7? Yes.
So I haven't considered those specific bands. There have been other studies that have looked at the potential for pause to act as a carrier of AME that have looked at, for example, the 12 micrometer feature. So for example, WISE band 3 is dominated by PAW emission in the 12 micrometer band. And so they found that PAWs were not the best, sorry, they were not the best tracer of AME. One reason that we specifically selected this band, and I'm glad you asked this because I forgot to mention this, but one reason that we chose this is that we expect this feature to trace the smallest PAW species. And we think the smallest grains are the ones that are most likely to produce the AME at roughly 30 gigahertz.
Okay. Okay.
This seems painless.
Yes.
So you had a very nice plot where you showed, was it for Orion, spectrum of the AME picking. So I'm looking at that. That's beautiful to me. And I'm thinking, so what you're finding, the bottom line of your work, is that it looks like so PAS might be responsible for AME in some regions of the sky and some others not. So when we produce spectra like the ones that you show, is there any spectral indication? So what that high quality and that resolution, is there any indication that these spectra are diverse? So because if there are very different mechanisms for producing AME in different parts of the sky, then you would expect them to not look very much alike. So is there any indication when we're looking at spectra like that for this diversity?
That's a really great question. It's not something that I've looked into yet. So the AME map that we were using to perform our spatial correlation analysis was evaluated at a single frequency, 30 gigahertz. And so this is based on the Planck best fit to a two-component AME model. But we haven't actually looked in detail at the spectra yet. As far as I know, I don't think we have the sensitivity quite yet to distinguish between some of these AME models purely based on the spectra. But we definitely want to look at different environmental factors. And I mean, it could certainly be interesting to look at how the spectra compare with these correlations. One thing we did briefly consider was the width of the AME spectrum specifically. So we did try to see if there was any correlation between the regions that favored pause as a carrier and the width of that spectrum. But we didn't see any strong sign of a correlation there.
A similar question is, do you have any feeling about differences in the excitation mechanism of the pi emission in the different regions of the sky? Because you are looking away from the galactic plane, so certainly it's not young stellar young stars. So it's probably the interstellar radiation field or something else. So do you have a feeling of variations in the excitation mechanism, which may give you a hint about what is exciting the AME emission in those regions?
Not so much yet. That's something we wanted to look into more in the future. But we haven't investigated that yet. But yes, we do think that PA emission mechanisms can vary significantly depending on the radiation environment.
Exactly.
So that definitely could be part of it. And essentially, we suspect that just the variations in those different radiation field environments would suppress the correlation with the PA emission, where it wouldn't suppress the correlation with thermal dust. So it's possible that if we took that into account, that pause could be more strongly preferred as a carrier for AME.
So, can you go back to the map, the paper map of this D3 band thing where you cleaned it for the zodiacal line?
So this map?
There, yes. So I can still see the zodiacal light there, right?
Oh, so sorry. This is the actual zodiacal component that's
Sorry,
fit.
go to the other one where you actually saw the.
Oh,
There.
yes.
So I can still see the zodiacal light.
Yes, yeah, so there is still some sort of residual along the ecliptic, and there's a good chance that is due to residual zodiacal emission. It shouldn't have any impact on this analysis because most of the sources that we looked at are far from those regions. So like this is like where these sources are located. None of them really lie near where that residual
No,
zodi is still showing up.
That's fine. My question is, does this mean that there are PAHs in the interplanetary medium? I mean, and is there a reason why there shouldn't be any?
That is something I've wondered about, but I don't know the answer to that. But it's definitely an interesting question. But I mean, there's definitely something there, right? That seems to, lie in the ecliptic plane. But I don't quite know why that's occurring.
So there were never detected in the interplanetary medium PAHs?
I don't actually know if they've been detected in the interplanetary medium.
Actually, just out of curiosity, can you detect them in the atmosphere? I mean, certainly some in the atmosphere.
That's a good question. I don't know if this would be sensitive to any pause in the atmosphere, but that's a good question. I don't know.
But is there satellite?
This is space.
This is.
Oh, right. So this is, yeah, these are space-based observations. I don't know if ground-based observations would have to account for pause in the atmosphere, though. It's a good question.
Could this be an artifact of the fitting method that they're using? Because you're using 3 solid models, but certainly there could be variations of the interstellar spectrum, for example, across the sky, or there could be variations of the zodiacal light, depending on which location of the ecliptic we're looking at.
Yeah, sorry, I didn't give quite the best explanation. So for the zodiacal component, we use the Kelsall zodiacal model, and this model does change over the sky. So we do actually use different spectra in each pixel on the sky, and same for the faint source model. This is also evaluated within each pixel. It's only the PA component that stays the same. Yeah. But yeah, we're fitting the exact same spectral model for Zodi that was originally fit for, to remove it from these maps. But since we're also fitting this new component of the Apollo mission, we were just trying to sort of account for any over or under subtraction there. Yes.
So that you are, thanks for the presentation. You are detecting most of the regions along the plane of the galaxy, right? Then you are like the effect of dust attenuation itself. Do you think it plays a role at all in because AMEs are in this millimeter, right? Why
Yeah.
3.3 micrometers? I mean, it's an order of magnitude less extinction than in the V-band, but still, if you look through the plane of the sky, through the plane of the galaxies, that's a lot of dust.
Yeah, that is true. So something that we're planning on looking at going forward, when we try to do a more complete full sky analysis, is to look at the correlation with extinction also. So that's something we want to look at, but it could definitely have an effect.
Okay, I'm seeing a person in line, so let's send them again.